In this video lecture, I'm going to discuss the nature of light, and specifically in the ways in which we need to understand light in order to understand the quantum mechanical model of the atom. So first I want to talk about the wave-particle duality of light. Would we call light a particle or a wave? And is it possible for something to be both a particle and a wave? And when would something be acting as a wave and when would something be acting as a particle? And so you've actually experienced both waves and particles in your life. Waves you might be most familiar with thinking about water, but you've also probably experienced or talked about light waves in your physics and chemistry classes prior to this one. And you definitely have seen particles if you think of just like throwing a ball against a wall. That is something that's behaving like a particle. And so we're going to talk about light and how we would define the properties of light. So light, or what we would call visible light, the colors that we're used to seeing, is a form of electromagnetic radiation. And so what that means is there are two components. There's an electric field component, and that's illustrated in this picture here as a red rectangle with a red wave. And then there's a magnetic field component rotated 90 degrees, so it's perpendicular. And it is shown here in this blue rectangle and the blue wave. And both waves are traveling in the forward direction. The magnetic field acts on magnetic particles, and unfortunately the best definition that you're going to get at this stage of your education is it's a magnetic particle if it interacts with the magnetic field. I know that's a terrible definition, but just know that the magnetic field comes from charged particles that move, so it's the motion. The electric field is just the charge itself, so it just acts on the charge. And electromagnetic radiation has both components, hence why we call it electromagnetic. Light beams are collections of electromagnetic waves. And I'm going to go through the wave definition of light now. This can kind of show you a little bit, this is like a moving version of this figure here. So this might help you understand what it looks like. So a particle could travel in this direction. So I want to specifically focus on amplitude, wavelength, and frequency just to give us a quick review of these terms. So amplitude is the height. So it's from the middle, from this base part to the peak or to the trough, so the amplitude. The wavelength is the distance between two equivalent points on adjacent waves. So this is not one wave right here. This is actually two waves. One wave starts here and it ends here. So this would be one wave, and then a second wave would start here and go. So the amplitude is the height. The wavelength is the distance between two equivalent points on adjacent waves. Frequency is the speed at which the wave travels, so the distance traveled in 1 second, and so it's kind of proportional to speed. So you can imagine if I'm standing right here and I watch how many waves pass me in 1 second, that's my frequency. And so you can see that as the wavelength is longer, fewer waves are going to pass by in a second. If the wavelength is shorter, more waves will pass by in a second. The units for amplitude, that would be, it's a distance. We don't really talk as much about amplitude, but wavelength, those are distances for sure. So you'll see a lot of times nanometers or meters, and frequencies units are hertz or per seconds. So amplitude is really just intensity. So bright light has a higher amplitude, dim light has a lower amplitude. Notice how these two waves are identical in everything except amplitude. So the same frequency, the same wavelength. Color is what's determined by wavelength. So the longer the visible light wavelengths, those are red, and goes then orange, yellow, blue, indigo, violet. So shorter wavelength, blue. And then intensity is amplitude. And then this is also true for sound waves. So sound waves, pitch is the frequency, and amplitude of the sound wave would be how loud it is. So let's think about how these are related. So if you have a long wavelength, that means a low frequency. Those also have a lower energy. Whereas a wave with a short wavelength would have high frequency, and it also has more energy. You can think of it as a wave that hits a lot of times in a second. That's a lot more energy that's being transferred. And so if you have a low frequency, low energy wave, long wavelength, what that causes is molecules to vibrate or move. It doesn't break any bonds. There's not enough energy to break the bonds. This is actually how microwaves work. So a microwave hits your food with microwaves, that's why it's called a microwave, and what it does is it causes the water molecules in your food to vibrate, and those vibrations generate heat, and that heat heats up your food. So low energy, you're not going to get cancer or anything, we're not breaking any bonds, but you are creating motion. High energy light can actually break chemical bonds. So if we're talking about UV light or X-rays, when they hit molecules in your body, like skin cells, for example, they can break some bonds. And then those bonds, like in your DNA, can rearrange, and then when your next skin cell divides, it might be cancerous. So that's how ultraviolet light, with its high energy ability to break bonds, can actually cause things like cancer or other diseases. And gamma rays, this is a form of radiation that we consider very harmful because it can cause a lot of damage, and it's because it has so much energy it's breaking bonds. So radio waves and microwaves have very low energy. They can't really do anything to you, whereas these high energy actually have enough energy to break bonds, and so then these would be considered much more harmful. So let's think about what happens when two waves encounter each other. So two waves that are perfectly in phase, when they hit each other, what they will do is called constructive interference. So they constructively interfere, so you just get double the wave. If they're fully out of phase, they destructively interfere, and then you get a flat line. So you can think about this as looking at every point on this, like every point on the graph, and adding them together. And then you'd get this. So if you were to draw this on graph paper and add all the points together, you'd get this. If you subtract them all, you'll get a flat line. So let's take a look. Remember that waves are constantly in motion. So let's take a look at what would happen if we have two waves that aren't perfectly in phase. So we have this stationary wave here, and we have another wave, and you can see that when they fully line up, you get that constructive interference, and when they cancel out, you get that destructive interference, and then you'll see how the wave, there are points where it's not double the initial wave, and it's also not flat, right? Because you've got this gradient. So what might that look like if we were to take a picture of that? Well, before we talk about that, I want to just mention this concept of diffraction. So waves can bend around objects, and particles cannot do that. So when you have a wave and you send it through a slit, you get this diffracted wave. So we're going to see what happens if you have two slits. So we're going to look at diffraction and interference. And I just want you to remember that if you have a particle, particles cannot do this, right? If you have a ball and you throw it at a wall, it's going to bounce right back at you. It won't bend around it. But light doesn't do that. If you shine a flashlight at a wall, it doesn't zap right back into your eyes, right? It just bends around the wall. So let's take a look at what happens if we have diffraction and interference interacting together. Well, you have a light source, and it's going out in these waves, and then goes through the slits. Now the slits create two waves, and they can interfere with each other either constructively and give us double the wave and a bright white spot, or they can give us no wave, a dark spot. And then you see how you've got this gradient, you've got that gray. So this is a picture, if you were to imagine visualizing this on film, like a piece of photo film, this is what you would see. All right, so light is a wave, but you've probably already guessed that light can also be a particle, or you've heard this before, the wave-particle duality, the wave-particle duality of light. So the photoelectric effect, this is where we see light behaving like a particle. So if you shine light at a piece of metal, if it's of the right frequency, electrons will be ejected. So think about that. We just said that light does not act like a particle when it hits something. It diffracts, it bends. But this isn't showing light bending. This is showing light hitting an object and sending it off in another direction, like a pool cue ball hitting a pool ball and then it moving, right? So this is actually what won Einstein his Nobel Prize. He proposed that a beam of light was really a stream of particles that we now call photons. And the energy of a photon is the product of Planck's constant and its frequency. So I'm going to show you what that means. So energy of your photon, you take this h, Planck's constant, and frequency. And so the number of electrons ejected is proportional to the intensity of the light. So as the intensity gets bigger, as the amplitude gets bigger, more electrons are ejected. The wavelength of light tells you how fast the electrons will be ejected. So lower energy light will eject electrons with a lower frequency. Higher energy light will eject them with a higher frequency or a higher velocity. Now, there is a minimum frequency threshold. So again, wave-particle duality, minimum threshold. So if you are below the minimum threshold for frequency for a given metal, there are no electrons that are kicked off. So potassium, the minimum frequency for an electron to be ejected, the light has to hit it with the energy of 2 electron volts. You don't need to worry about the units yet. We'll talk about those later. But so the red light, which has a frequency of 1.77, that's not going to eject an electron. But as soon as you get above that threshold, they're going to eject electrons. So you can see how light here is acting like a wave, and light here is acting like a particle. Okay, so this little picture right here kind of tells you exactly what Einstein won his Nobel Prize for. It was the photoelectric effect. Okay, so that was a brief review of the wave-particle duality. So let's think about, why do we even need to think about the wave-particle duality? Well, that's where it comes in with the emission spectra. So we're talking about an atom now. So not an electron, not a particle, not a photon, but a full-on atom. So here we have our nucleus, and here we have these energy levels. So if you have a glass tube filled with hydrogen gas and you shine electric current through it, you'll see light. You have actually witnessed this before. Any of those neon light advertising signs, not the digital LED ones, but the ones that are tubes filled with a gas that lights up when hit with a charge and you can hear them buzzing. Pretty much mostly found in dive bars now. So those are tubes filled with a gas that light up when they're hit with a charge, with a current. And each element has its own fingerprint. And so this is the fingerprint for hydrogen. If you were to a slit, put the hydrogen light through a slit, you would see a violet line, a blue-green line, and a red line. And those correspond to electrons jumping between discrete energy levels. Okay, so again, this observation of these quantized levels is what led Einstein to think, there must be some sort of particle behavior for light. And there must be some sort of particle behavior for electrons. And so what this is showing us is that if you have an electron that's jumping between these energy levels, you will see light of a given color, meaning it corresponds to a given wavelength. And that wavelength also corresponds to energy. So that is just a really quick overview of the nature of light. If it went fast for you, then I do suggest that you go back through the book and you do some practice problems and review this. But in our next few lectures, we're going to break these things down and work with them and solve some problems related to the hydrogen atom and looking at the wave-particle duality of both light and electrons.